the radiated light from the magnetic pole. Hello?
Okay, yeah. Okay, I think I shouldn't take more time. We can yeah, just let's just go ahead. I think.
Thank you, ma'am, for your questions.
Okay, ma'am. Thank you, ma'am.
All right. So, any other questions from the panelists or the judges? Okay, so I guess none. So now coming on to the second last team, we have the eighth team in the line, and that's Vibhor Singh and Aditya Rao. So the problem statement was from field theory, and the question was designed by Tiasa Kaur. So I would like to hand it over back to Vibhor Singh and Aditya Rao. Guys, it's all yours.
Is my screen visible?
Not yet. It's not visible as of now.
Yes, it is visible.
Okay, then yeah, it's visible now. Yes.
Okay, fine. So, the topic that was given to us is a field theory. So basically, what the problem abstract is, I'll summarize it. We were given a Lagrangian for the field, and we were asked to analyze it, and we were asked some questions about the field. We mentioned that there is a vector which
Aditya, your voice is breaking.
Yeah, I guess I guess there is some sort of technical glitch from Aditya Rao's side. Is it's probably with the network. So meanwhile, while he's back, I would suggest Vibhor to take over.
Yeah, okay. So I think he's back. Aditya? Hello?
Yes, he's here in the lobby. Yeah.
So I'm starting. Hello.
Hello, am I audible?
I'm audible?
Yes, Aditya, you're audible. Please carry on.
Should I continue?
Yes, please.
Okay, so the equation of motion that we got after solving the Lagrangian turned out to be this, which is specified right here. So
I'm sorry to interrupt. Are you presenting your screen? It's not visible to me.
Okay, wait a sec.
Aditya, can you start from the beginning?
Is it visible
yes,
now?
Yes, please proceed.
Okay, fine. So from where I was not audible or whatever?
From the beginning itself.
Hello?
Yeah, you can start from the beginning, no problem.
Okay, fine. So, okay, thank you. So actually, what we were asked to do was we were given a Lagrangian, and we were asked to analyze that as Lagrangian and speak something about the fields. So the first question that was asked was to name the vector that would give the Lorentz transformations of the field, and also which would define the entire field. These vectors are called the polarization vector potential. So when we expand the vector potential A mu in terms of Fourier transformations, we get some vectors which are called as polarization vectors. These are the four
Vibhor Singh, I would suggest you that by the time your teammate is back, you continue, please.
Yeah. Okay. Hello. So I'm starting right now. So basically, what we're asked to do is we are given a Lagrangian and we are asked to analyze it. So I need a presentation to begin with. So Aditya, can you present the screen?
Okay, wait. I think my net is acting up. Internet connection.
So basically we are given with a Lagrangian and we're asked to analyze it. And so can you show the Lagrangian? Yeah. So here is the given Lagrangian and the
Is it
Lagrangian.
visible?
Yeah, it's visible. So uh, we are asked four questions, and the first one of them is the where you can see a mu as a four vector. So upon the mode expansion of that vector, we'll get a vector which is responsible for the Lorentz symmetry of this, and we are asked about the vector. What is that vector? So the answer corresponding to that is it is the polarization vector, and represented by epsilon mu r. The polarization vector is orthonormal, and uh, it spans the space. So, so what basically we have done is we solved the Euler-Lagrange equation of that Lagrangian, and it took a couple of while to do that. But what we get a final equation was something minus.
Could you please share the screen?
Actually, sorry for that, but I don't have the control of the screen.
Sorry, what happened is that it's raining a lot here, so my network is acting up. I'm getting disconnected from the call. Is it fine now?
Yeah. Uh, Go to the Euler-Lagrangian formulation. That particular slide. So what we did was we applied the Euler-Lagrangian equations, and we tried to derive the motion of we tried to derive the response of the particular
Fine.
field. So
Yep.
what we get the equation was something of del square mu a mu plus the something equation. So the main thing was to derive the polarization vector from there. So uh, taking the assumption a mu a plane wave solution, that is a mu is equal to epsilon mu exponential of iota kx, that is a solution of a plane wave. Putting that into the differential equation, we'll get the equation of polarization vector. But that's but the equation which was there, that was too complicated for us to solve because we are getting mixed up with the indices. So we left the equation in between. And what we are trying to say is that by putting the plane wave solution from the polarization term, we can get the polarization vector from there. And the next thing, what we are asked to find out the scattering matrix for the problem. So scattering metric is something when if we multiply it with the initial state, we will get the final state. So some scattering metric has to do with the interaction term. So when we looked at the Lagrangian, we didn't find any current density term. So what we conclude from there, that there is no interaction term in the Lagrangian. So basically the initial state and the final state has to be the same. That means the scattering matrix we are going to get is an identity matrix given by the equation on the slide. So, and the final thing which we are asked to do is to uh, analyze the Hamiltonian of the system. So first of all, we find out the conjugate momenta of the corresponding field represented by pi mu that we got there. And if we look for the time component of that, we'll find that pi not equal to 0. So that condition works as the uh, primary constraint of the system. And if we take the Hamiltonian, if we take the Poisson bracket of with the Hamiltonian, we'll get the secondary condition and secondary constraint. So what we by doing that, what the secondary condition we got was something like that: half e squared tau epsilon mu rho del mu zero equal to 0. So that was what we did in the Hamiltonian analysis. So basically, the Lagrangian which we were given comprises of the electromagnetic four vector potentials. So the four vector potential has the term upon the mode expansion, we will get a vector that is responsible for the Lorentz image. So we were asked what is that vector. So the answer for that question is that is the polarization vector. And the next thing which we are asked to do is to derive the polarization vector for any given momenta. So what we did was we started from the Euler Lagrange equation and derived the equation of the reaction of the field. So finally, by putting the plane wave solution of that thing, we will get the polarization vector. But the max that will be used will be too rigorous. So instead, we are having very difficulty with that. So we just left the equation in between. And we just concluded that by using this plane wave solution, we'll get the answer. And the scattering matrix, what we got was the identity matrix, and we did the Hamiltonian analysis of the system, and we found the conjugate momenta and the primary and the secondary constraints of the system. Well, that's all from my side.
Okay.
So basically, the problem we faced is that we don't know that much about the electromagnetism and relativity. So we tried to solve this with whatever knowledge we had. That's it. That's what our conclusion is.
Okay. Thank you, Aditya and Vibhor. Okay. Going over to the panelists, please, if you have any questions, please ask. Yeah, sure.
May I ask? Yeah. So see your Lagrangian. So in your Lagrangian, you have two terms.
Yes, sir.
Do you know what are those terms correspond? You said that there is no interaction term. How did you conclude that there is no interaction term? If there are no interaction terms, then what about these two terms?
The first term is the F mu nu tensor, which is called the electromagnetic tensor, which comprises of all the electric fields and magnetic fields as their components. So it defines the electromagnetic field basically. And the second one contains a mu, which are called as vector potentials for the electromagnetic field. And these both terms are, the F mu.
Just a minute. F mu nu is equal to del mu nu minus del nu nu. So where is a field corresponds to what? Electric field or magnetic field? What kind of field you are talking?
It's basically Lagrangian corresponding to the electromagnetic field, some sort of wait a second. It's some sort of configuration of the electromagnetic field itself.
No, fine. But what is the physical significance of this term? Lagrangian is connected with some term, of course, which are having some physical significance. Do you understand that?
Yeah, I get it.
And what
Actually,
about
according to what I
But
think is the first term of the Lagrangian which was there, it contains mostly the information about how the photon would react in that field. But it describes the behavior of the photon in the field.
which field?
Electromagnetic field, the photon.
How the photon behaves in the electromagnetic field?
Yes.
photon
I'm not
behaves.
so sure, but it's certain thing I can say.
Uh, how the photon behaves within the electromagnetic field. Is that your statement? And
Yes.
I
what
I
about
I believe I believe that not all Lagrangians correspond to physical situations. We can construct any sort of Lagrangian for a system, and it is not required that it should correspond to some physical
no?
system.
Looking at the Lagrangian, you have concluded that there is no physical interaction. There is no
Yeah,
interaction.
I mean the Lagrangian does not interact with any other fields because generally any interaction term is introduced by using a current vector. I mean current vector field. But I don't. I mean, we don't see any current vector field in this Lagrangian. Like in the normal, the Lagrangian which was used to derive the Maxwell's equation, there was a current vector which was called the J mu. That was the interaction term. But here we don't see any interaction term as such. So that's why we said that there is no sort of interaction, and the scattering matrix is the identity matrix.
No, your conclusion is right. There is no interaction term in the Lagrangian. That is fine. I'm trying to see that how much you really you understood this Lagrangian. And what about the second term? Second term of the Lagrangian?
Um, but I don't think it doesn't. It does correspond to any sort of physical systems. I'm not sure about it because
Why
the
is it?
first thing is that we don't know much about electromagnetism as we never had it in our course. We're going to study it further. So, with the limited knowledge I am having, I think that it does not correspond to any physical system. I suppose.
Okay, so but A, do you have any idea A stands for what?
A
Field.
is the field potential.
Field potential.
Yep. I mean, yeah, field potential vector.
But finally, you have said that A is a polarization vector.
Now we call the epsilon the polarization vector, and that we obtained by putting the plane wave solution for A mu in the Euler-Lagrange equation we obtained.
We are not
Okay.
saying that the A is the polarization vector. What we are saying is that upon the mode expansion of A, we get a vector called epsilon mu, and that vector is responsible for the Lorentz invariance, and that's what we call the polarization vector.
Okay.
Okay, thank you, sir. Any other questions, judges? Okay, so I guess we can move over to the next presentation, the last one. It's the presentation by Vedant and Rohan Tangaraj. Their problem is from optics, and it was again designed by Ramkumar Radhakrishnan. So Vedant and Rohan, please take over.
Hello, good evening, everyone.
Yes, Rohan, go
Am I
ahead.
audible? Yeah. So we are team 9. Our topic in Researchathon is optics. So the problem provided to us was we've been given an equation, and we have to find what that equation is, and we've been told this equation has some connection with the minimization of area, We've also been told something about equation 2, which has not been mentioned. We have to find what that equation is. So these are the topics that we are going to go through. So quantum mechanics, it's a paradigm shift in physics. Many Nobel scientists consider it to be a revolutionary field of 20th century. It was from Thomas Young's double slit experiment that we proved wave nature of light, and Albert Einstein's photoelectric effect proved the particle nature of light. So we think light is a wave or a particle. But long back, there has already been a classification in optics, geometric optics and physical optics. Geometric optics is based on ray concept. It's not particle, just a geometric construct. And it doesn't account for interference or diffraction. While physical optics is based on the wave nature and it explains the diffraction, interference, and polarization. So now we just talk about Iconal equation. Iconal equation is the bridge between geometric and physical optics. It's a non-linear partial differential equation. The Lorentz invariant Iconal equation is of the form delta S square is equal to 1 by C square del S by del T whole square, where this S is the wavefront in the face of geometric optics. While in scalar, the scalar Iconal equation is of form del S whole square is equal to n square, where n is the refractive index of the medium. So my teammate Vedant will talk about how Iconal equation bridges wave equation and geometric optics. Over to Vedant.
So hello. As my teammate said, now we will derive what is the bridge, how it is a bridge between wave and geometrical optics. So as we know from electromagnetic wave equation from physical optics, which is the equation 1, let us consider that solution to be AEI omega power, which is the capital T represents the travel time. And if we substitute this assumption in our electromagnetic wave equation, we get the following equation 2, and further simplification will give us that del T the whole square is equal to u square, and u square is nothing but of 1 by v square. So this is nothing but the travel time gradient, and if you multiply c square in both sides, you will end up in the Iconal equation, which is del s the whole square is equal to 1 by c square del s by dou s by dou t the whole square. Now similarly, from geometrical optics point of view, if we use the Fermat principle, it says that given 2 points, the light travels in a minimum path. If we use that equation, we get the condition for a ray. We get a condition for a ray path, which is equation 4. And from Eigen's principle, which says that there is a surface which propagates in the direction parallel to its gradient. So from that concept, we get the equation 5. And if we substitute equation 5 in the previous ray equation, we come up with the Iconal equation, which is del s the whole square is equal to n square, which is the scalar Iconal equation. And by applying Lorentz invariance in it, we get the del s square is equal to 1 c square dou s by dou t the whole square, which is the Lorentz invariant Iconal equation. Now, regardless, we derive both equation from both points of view. Now, what this physically means. In the wave context, this S means a phase in the wave point of view, whereas in the ray optics or geometrical optics point of view, this S tells us about a variable which is called Iconal. There is a surface parallel perpendicular to the direction of propagation. So since the same equation have different interpretations in ray optics, geometric optics, and physical optics, this forms a bridge between both based on the interpretation. Now let us use this Iconal equation to apply. So we apply this for refraction, to apply this for refraction, let's assume two medium, medium 1 and medium 2. Um, in this boundary, let's assume a small loop and let's integrate del s in that loop. If we did do that, and if we, while doing it, when we reduce the volume, surface area to infinitely small, then the perpendicular component gets cancelled out and only the tangential component remain. So if we calculate that, then we are end up in the Snell's law of refraction. Similarly, in the from this law, if you want to define reflection, then since n and n dash will be same, so you end up in sine alpha is equal to sine beta, then you will get alpha is equal to beta, which is the reflection condition. Now over to Rohan.
Yeah. Thank you, Vedant. So this equation is actually very similar to the wave equation. The wave equation is a second order equation, while the Iconal equation is a first order second degree equation. But what is the difference between both? The difference is wave equation can undergo superposition, while the proof for that is here. We assumed A to be A sine kx minus omega t plus B sine B cos kx minus omega t. And while trying for superposition in Iconal equation, we find that superposition is not valid. So in summary, the questions asked to us was, what was the equation given, first equation? It's the Lorentz invariant Iconal equation. And the second question was, how do you prove that Iconal equation is a bridge between physical and geometric optics? Iconal equation is derivable from both geometric and physical optics, and this proves that it's a bridge between the physical and geometric optics. Next question was, what is the equation that is very similar to this and is found everywhere? Wave equation is the equation that has similar properties. And next question was, what is the common basis for minimal surface problem and Iconal equation? The common basis is calculus of variation. They both are based on the calculus of variation. We have been asked to use Iconal equation to prove any property of light, and Snell's law was derived using the Iconal equation. And the final question was, what is the main difference between equation 2 and equation 1? That is wave equation and Iconal equation. The main difference is wave equation is superimposable while Iconal equation isn't. So these are the references. Any questions?
All right. So panelists and judges, if you got any questions, please.
I think, hello.
Yes, sir.
Vedant, I think
Yeah.
the first presenter was Vedant, right?
No, it was Rohan.
It was me, sir, Rohan.
Okay, Rohan. So if I'm not wrong, then probably you have mentioned that geometrical optics can explain reflection and diffraction. So
I didn't mention it, sir. I just told it cannot account for interference and diffraction.
Oh, then it may
doesn't
be
account for interference and diffraction.
Okay. So fine then.
All right. So I guess, yeah, this was an amazing presentation from the last team as well. Now, meanwhile, I guess all the judges and the panelists, all the judges have filled out their response sheet on the Excel sheet that we forwarded them. So I request you that if you haven't filled it, please fill it ASAP so that we can add up all the marks and then we can go for the final approach. Meanwhile, I would like to that like we need to have sort of feedback session from the participants right now. So the team one, yeah, like I would like to mention this one thing, that during these 30 hours, right, the people who made the question designers and the participants, they were in constant touch with each other, just to make sure that in case of any sort of any kind of glitch or any sort of problems that that the participants come across, the question designers are always there to help them out. And we had a sort of mentorship session in between, like at in the morning, in the afternoon, and in the evening, and even at night at times when needed. So I'd like to start with team one, Brijesh and Navdeep. So guys, if we would like to have the feedback from you guys on your mentorship session and the type of question that you were given. Was that question good enough for you, or was there enough learning for you? Was anything new for you guys to learn about it? So
Wait,
please
Deepak.
let us.
Wait,
Mhm.
Deepak. Before coming to that, let me ask our panelists, our panel
Okay,
of
yeah.
judges, like how was the event? What do you feel about it? And if you find anything we can improve on, so please suggest us, please. Bhaswati Mukherjee, ma'am.
Yeah, yes. Hi. It's a very nice um, endeavor, I would say. I enjoyed it thoroughly. Uh, since you have asked like feedback, so we probably will take some of these into account when you plan the next year's event. So I thought that while some of the projects were really nice really nice in the sense that they explored things in basic and then went one step ahead, but some were actually the starting points were not very should have had been put at a somewhat more basic level. So and also like just working out certain things, and I think I can say that particularly say for the cosmology project, they really struggled, but if you had thought a little differently, it could have been. So it would have been a good idea to maybe involve some of us in the while you were going through the while you were setting up the problems, because there is always a graded approach to any research project as well. You just don't start off with, okay, you are given this concept and then you start, because it requires a basic research or means basic physics understanding. So yeah, so but I think overall the participants did very well. It's a really commendable effort from all of the participants and also all the organizers. I would say, like I can see that you have spent considerable amount of time doing this, and it's very, I would say, very inspiring to see. So a lot of young people doing science or being doing physics problems with so much guts. So anyway, so it's, and I wish you all of you all the best.
Thank you, ma'am. Thank you so much for your valuable words, and yeah, surely we will keep that in mind. Okay. Okay, Monoranjan Guchait, sir. So, do you have any suggestion for us?
Yes. First of all, I really appreciate, I said in the beginning, so your effort is really commendable. You have tried your level best to do an event like this, and it is really, it has, I believe it will have immense, in fact, influence in your university among the students. And I'm very happy to see the enthusiasm the candidates they are having, and they prepared. They were given 30 hours. I think 30 hours. Many of them are saying that 22 hours they have worked. It is something really fantastic, and I believe it will inspire them to do physics as one of their career. And And about the selection of the problem, yes, some of the problems it is very nice, but in general, what Bhaswati has already said, I also say some having the same view. I think you decide the problem in such a way that the background will be your classroom lecture. Whatever you read in your class, either in BSc or MSc, and from that background, you design your problem at the advanced level. Either some instrumentation related, designing some experiment, something like that. Not something somebody said that they are not aware of it, they have not studied it before, something like that. It is true. In the last 30 hours, you cannot do many things. Okay, so which will have more thought provoking. Whatever knowledge you have, using your knowledge, you just put your thought and give the answer. That type of problem you decide, not how much knowledge you need to do this problem. I think you when you will decide the problem, you just think along that way, and I think you will be able to do this, because I see you are making a big effort, and I think you are inspired to do this. So thank you very much for all these things, and I really wish success this program. Okay, it is already done, and in future also. Okay, that's it.
Thanks a lot, sir. Thank you for your valuable feedbacks. We'll definitely take them up. And now, Dr. Devesh Roy, sir, any feedback from your side?
Yes, first of all, I will thank so much to Deepak, Yash, Ramkumar, and all team for the Patak for organizing and giving us organize such a nice event and putting there a lot of times and efforts and all this. And secondly, the participant probably, and that's why I asked somebody, a couple of candidates, how much time you have spent. And I think I'm sure that all the nine teams, that is 18 candidates, participants spend there most of the time for the last 30 hours. And that's what actually reflects how interested are you in physics. And I am sure that you are essentially the stars of the next generation, of course. And as Dr. Vijay said, I also agree with that. The problems maybe we can devise in such a way next time, and that which will be based on already existing knowledge. For example, let us put a benchmark of second year physics, second year undergraduate physics, as the topics covered by until that Markland. Based on that, you can put up a problem which can, at least the basic knowledge will have for all the participants, and they can design or solve the relevant problems given to them. Probably that will make more enthusiastic the candidate and more comfortable to find out new information. And of course, they'll be also encouraged in research. I mean, it should not be probably you can look on that. It should not be just to win a quiz for certain time period, but also we need to motivate physics for solving future useful problems. And that's what I pointed out. And of course, another suggestion is we may continue this through online mode to get national level participants. We should not be confined within our institute. Maybe we should extend the opportunity for other candidates across the national, across the country. So that must make our event more successful and more interesting, and also that will also increase fame of our institute. That's I think. Thank you. Thank you very much. I wish all the best for all the participants and organizers, you guys. And thank you.
Thank you very much, sir. Thank you. Thank you. Now moving on to Dr. Unni Krishnan. Sir, would you mind a few words or few advices?
No, I have not much to advise. I think it was a well-conducted program in the sense you could bring together talented students to solve problems, very hardworking.
Hello. I guess there's a network problem again from Dr. Unikrishan sir's side. Am I audible first of all?
Yeah, you
Yes,
are.
you are.
Okay, thanks. Because at times when everybody's silent, it feels like I have a connection issue. So, all right, no problem. Meanwhile, Dr. Unikrishan sir joins us. Okay, I would request Dr. Kian Patak sir to just say a few words of advice to the young budding researchers today that we have in the country.
Yeah, thank you, Deepak, very much for your kind words. And actually, well, this is difficult, because none of us, at least the senior people, have been, grinded for 30 long hours and solving the problem. So probably, we cannot really estimate or understand the psychological, pressure these people must be in. That is one thing. And so under those circumstances, these people have done wonderful job. We must appreciate. And so all kudos to the participants, of course, and organizers, of course. You people have done a great job. Second thing, as regards to the toughness or the level of the problems, uh, probably, this has come because we are in the third round of this researchathon. First was the elimination round, and second was the selection round, where we have exposed them with more basic questions, but they had to do it at a rapid pace, and then we selected this thing Q. So in a sense, we have rather understood that they are, most of the students are at a particular level, and based on that, I think we have designed our problems of this level. But yes, uh, we can always have a brainstorming session about the suggestions put forward by the eminent judges. And one of the wonderful suggestions I think Bhashwati ma'am has given, that we can always include these people into our designing of the problems. So, they can always help us out in refining the questions and kind of the things where our understanding would be lagging. So that that part we will definitely take into consideration in our all future endeavors. That we will be in touch with you people all the time, and we'll take a lot of inputs from your side about the design of the problems or design of the questions and other things. This is also my duty to, I have to, in a sense, express my vote of thanks. So if you permit, Deepak, I will do that now itself. Uh, so, I must appreciate the participants, of course.